Welcome everyone. Today's video is all about quantum era computing redefined. We'll start from the basics QNN model architecture. So in quantum neural networking, we have this kind of architecture. This is quite analogous to the architecture that we have studied in deep learning, but it is not just like that only, but whatever you are looking at in the quantum neural network model, you will find that initially we have input layer here, then we have hidden layers which are of course quite big and are interrelated with the input layer and the output layer at the extremity. In quantum technology, we have zeros, or not zeros or one, but a superposition of both. So we talk about qubits here. To be specific, quantum computing stands at the frontier of technology, leveraging quantum mechanics to surpass the limit of classical physics. You must have studied about classical physics now, those Newton's laws and things like that. But here things are quite different. Here we talk of qubits and their entanglement, which can be achieved via quantum gates, links qubit in a way that makes them inseparable, enabling powerful quantum circuits. Core concepts like superposition, quantum tunneling, and entanglement define the true potential of these machines. If we talk of changes associated with quantum technology, challenges are the major ones like noise and errors. If a system is disturbed by noise and error, then we must find out ways. Let us talk about disturbances which are responsible for the challenges for the quantum computing. These disturbances includes but not limited to heat, electromagnetic radiation, cosmic rays, and all these things collectively referred to as a noise. It can disrupt the quantum states of qubits and lead to errors during calculations. Scaling quantum neural networks is particularly challenging because the risk of noise-induced errors increase as more qubits are added. See, whenever we are scaling quantum neural network or QNN, we generally add qubits and this induce errors. Then how to ensure resistance of the network to noisy data? We must include some features like quantum error correction codes, logical qubits, or environmental isolation. The latter works best in case of magnetic and vibration shielding, as it minimizes the impact of external noise and disturbance. The above two are also reliable. These codes distribute quantum information across multiple qubits to detect and fix errors caused by noise. Whenever we talk of logical qubits, we combine several physical qubits to form a single logical qubit. This is a approach that significantly improves stability and reduces susceptibility to noise, making it ideal for QNN. Here we have a graph which depicts the relation of noisy pairs and cost. So the impact of the number of noisy pairs to the robustness of quantum neural network is depicted below. Higher the number of noisy pairs, lower training and testing costs, which leads to greater robustness, which is desirable. The increase in the number of noisy pair enhance the robustness of the QNN model, as you can see here. You can see the cost is getting uh, approaching to 0.54, 0.5 whenever we move higher on the x-axis. The quantum world computer excellence in the real world using ML approach. See, the extended field, which is quantum reinforcement learning, aims to utilize the power of RL agents that rely on quantum models of computer. Instead of doing thousands of epochs with Adams method, we can simply do one single epoch with QML. Na? This way the optimization challenge will get vanish forever, which is one of the biggest challenges we see in the case of deep neural network training. We could in theory test all possible states of weights at the same time and output that one particular state of weights that minimizes the loss function. We must focus on minimizing the loss function, because whenever we minimize the loss function, we generally optimize it, and which is desirable, of course. Then we would look upon how noise can distort data, which is a common problem in both classical and quantum system. But for the sake we are generally see, we generally ignore quantum system, but to be honest, quantum system are really very, highly underestimate. We must not underestimate quantum systems. Here I have written a simple Python code. You can simply type it in your Colab and you would see the effect of distorted data, which leads to the noisy signal. The amplitude gets fluctuated every single time. Thank you.